Okay, so let's start. So today we'll take 2 hour session. Let me share the. Okay, so today we'll solve 4 questions basically from real analysis or functional analysis. One is question number 47 from Gate 2018, and the other 3 are question number 34, 25, and 12 from 2019. Okay, so let me start. Okay, so today we'll solve Gate 2018 question. This is a question from functional analysis. It's question number 47. Let L2 0/0, be the Hilbert space A, Hilbert space of all real valued square integral functions on closed 0, 1 with the usual inner product, and phi be the linear functional on L2 closed 0, 1 defined by phi of f is given by this integral, where mu is the Lebesgue measure on 0, 1. Then you have to find the norm of this linear functional phi. Okay. Okay, so this is the NPTEL reference. This you can look into it. Okay, so let's try to solve this one. So L2 0, 1. So this is all functions such that integral 0 to 1 mod fx d mu x, this is the Lebesgue measure on 0, 1 square, this should be finite. And what is the norm? F L2 norm, it is defined to be 0, 1 mod fx square d mu x for half. And what is the inner product for f in G L2 0, 1? F inner product G is defined to be 0, 1 fx gx d mu x. Okay. Now here phi is a linear functional is given. So before that, for that we have to find the norm of this phi. So for that we will use the ridge representation theorem. So let me write it first. So I am writing it ridge representation theorem for this Hilbert space only L2 0, 1. So let T be a bounded linear functional on L2 comma 0 1. Then there exists unique G in L2 comma 0 1 such that T, which is mapped from L2 0 1 to R, is given by T of F equals to 0 to 1 fx gx d mu x with norm t, this is functional norm of t, is same as g of L2 norm of g. Right, so this is ridge representation theorem, saying that any linear functional on L2 0 1, it will be given by the inner product with some unique function g, and the functional norm of t is same as the L2 norm of g. So we'll use this to calculate the L2 norm of this functional. Okay, so here we have P, this is a linear functional 0 1 to R, which is P of F 1 by 4 to 3 by 4 3 root 2 F d mu, means fx d mu x. So in order to calculate the norm phi, first to use the ridge representation we have to show that this is a bounded linear functional. So let's check that why t is bounded, phi is bounded. To check phi is bounded linear function. Linearity is clear, right, by the definition. Phi is linear. Now let's check that phi is bounded, means phi of f. So this is 1 by 4 to 3 by 4 3 root 2 f x dx. 3 root 2 we can take it out. And this we have, I have also make less than 1, take the mod inside. So this is mod of fx d mu x. Now using Cauchy-Schwarz, by Cauchy-Schwarz inequality, so what we will get? So Cauchy-Schwarz inequality, this 3 root 2, so this should be less than. So we are applying Cauchy-Schwarz this with the 1 function. So this is 1 by 4 to 3 by 4 mod fx square d mu x to the power half times 1 by 4 to 3 by 4 1 d mu x to the power half. So let me write the Cauchy-Schwarz inequality. What is the Cauchy-Schwarz inequality? Yes, there will be easy. So Cauchy-Schwarz inequality. So it is saying that mod fx gx d mu x, suppose this is a Hilbert space over H. This is less than 1 over H mod fx square d mu x to the power half H mod gx d mu x to the power half. So this is the Cauchy-Schwarz inequality. So we have used this one. So note that this is the right hand side, you can write it. So what is the L2 norm of, what if you calculate this, what you will get? So this is the integration from 3 by 4 minus, so if you calculate this one, what you will get? 1 by root 2, I think. So 3 root 2, this will be 1 by root 2. And this I am dominated in by from 0 to 1, I make it because this is bigger, d mu x. So therefore what we get? 3, this is the L2 norm of f over 0, 1. So we get P of f is less than 3 times L2 norm of f. And this is true for all f in L2 0, 1. Which implies P is bounded linear functional. So we can use the Ridge representation theorem. So then by Ridge representation theorem, we can calculate its norm. Now we have to first write it in terms of, so this will be given by some inner product with some L2 functions as P of f, this is 1 by 4 to 3 by 4, 3 root 2 fx d mu x. This you can write 0 to 1, 3 root 2 and characteristic function of 1 by 4 to 3 by 4 x, let me write it, fx, this one with d mu x. Let me call it g. 0 to 1 fx gx d mu x, where gx is 3 root 2 characteristic function of 1 by 4, 3 by 4. So characteristic function means it's 1 in this interval, 1 by 4 to 3 by 4 and 0 outside. Okay. So first note that why G is in L2, not G is in L2. Why? L201. So let's calculate L2 norm of G. So what it will be if you put, so 3 root 2, so it will be 18, and because of this characteristic function the limit will be 1 by 4 to 3 by 4 d mu x. Means it will be 18 times 1 by 2 to the power half. So it's square root 9, so 3. So this is finite. So G is in L2. Now ridge representation thing is, so we get what we get. We get P of F is given by F in a product G, where G is in L2. And ridge representation saying that this P of should be given by F in a product G for unique G. So this should be the G. So by ridge representation theorem, norm of P will be the L2 norm of G. And we have calculated this L2 norm of G. What is this L2 norm of G? This is 3. So therefore, non-P is 3. Okay, so 3 is the correct answer. So therefore non-P is 3. Okay. So we have solved question number 47 from Gate 2018. Any questions or doubt? Okay, then let's move to the next question. Okay. So today we'll solve Gate 2019 question. This is a question from functional analysis. It is question number 34. So consider the subspace Y, x comma x, that x belongs to complex number, of the non-linear space C2 with norm infinity. If P is a bounded linear functional on Y, defined by P of x comma x equals to x, then which of the following sets is equals to this set? So this is psi r at the point 1 comma 0 such that psi is a non-preserving extension of phi to that linear space C2 with norm infinity. Where the 4 options are given, you have to check which one is correct. Okay, so this is the NPTEL reference. This you can look into it. Okay, so let's try to solve this one. So this question is related to Hahn-Banach theorem. So this is basically, so let me write the what is Hahn-Banach theorem. So it is saying that let every continuous linear functional f defined on a vector subspace M of a norm space this may be real or complex X has continuous linear extension f to all of x that satisfies norm of x equals to norm of that extension linear functional f. Okay, so what it is saying is that suppose a linear functional which is defined on a subspace M of a non-linear space X. So suppose this is X and this is M. So let's say this is X and this is subspace M. So suppose there is a linear functional defined on M. So it is saying that then you can extend this linear functional to whole of X without extending the norm of F. So with the norm preserving extension. So you can extend this linear functional small f to a capital F which is defined in all of X and the norm will be the same. So this is the Hahn-Banach theorem. Okay. So let's see here what we have. So here again this subspace is given Y to be this diagonal subspace. So C2 here Y is this X comma X such that X is a complex number. So this is a subspace of C2 with the L infinity norm. So what is the L infinity norm? Suppose this is x1 and x2. L infinity norm is supremum of x1 comma x2. And phi is a bounded linear functional on Y. Phi is a bounded linear functional on y defined by phi of x comma x is x. So phi is defined on y. Okay. Then let psi be the non-preserving extension of phi to whole C2. Psi be the psi be a non-preserving extension of P2 whole C2. Then you have to find this set. What is this? Okay. So psi is a so this is a so what is psi? So psi is a linear functional from C2 with norm infinity to C. So how the linear functionals on C2 look like? Let's see. So psi is a bounded linear functional on C2. So let's take some element psi of x. Psi of z, let's say z x comma y. So this how you can write, but these are all complex number x and y. So this belongs to C2. So it has a two basis vector, let u1 equals to 1 0. So then you can write psi of x 1 0 plus y 0 1. So as psi is linear, so it will be psi of 1 comma 0 x plus psi of 0 comma 1 y. So let's call it this to be alpha x plus beta y, where alpha is psi 1 0 and beta is psi 0 1. So this will be the linear functional look like. Psi of z will be alpha x plus beta y, where alpha and beta are complex number. So as this is the extension of phi, so as psi is an extension of phi, so if we restrict psi to y, this should be equals to phi. So psi of z, if we restrict it to y, so what will happen then? Alpha, so it will then become alpha x plus beta y, so it will x comma x, so then it will become alpha x plus beta x. So alpha plus beta x. and this should be y, a p, and p of x comma x is x. So psi restricted to y comma p imply alpha plus beta x is x, and this is for all x. So x should be, for x non-zero, alpha plus beta should be 1, because this should happen for all x. So alpha plus beta equals to 1. So let me call it 1. So we get one condition. Now there is another condition for the, so this is a norm preserving extension. So norm will be same. So norm of psi and norm of phi should be same. So what is the norm of phi first? What is norm of p? So p of x comma x is x. So norm p means supremum of p z, so that z belongs mod z with the sup norm, this should less than 1. And if z is in, and z should be in y. Z is in y means z with of the form x comma x. So sup norm of z will be supremum of mod x. So this is same as supremum of mod x and here the supremum of means supremum of, let me write it same. And what can be this? And because z is from unit ball, so this, so if this is less than 1 means this should be less than 1, right? So if this is as norm z sup norm less than 1 means supremum of mod x, this is less than 1, right? So this should be less than 1. And now we will solve that this is exactly 1. So also p of what is 1 comma 1. So this is 1. So means as norm p is less than 1 and p at 1 comma 1 is 1. So norm p is 1. So norm of p is exactly equals to 1. Now we have to check what is the, and also that, yeah. And what is the, now we have to check what is the norm of psi. We have to find norm of psi. So what will be the norm of psi? So as psi is a linear functional in C2, as psi is a linear functional on C2 with this inner L infinity norm. So psi belongs to this dual of this, right? So C2 with L infinity norm star. So this is the dual of now what is the dual of this C2 with L infinity norm? So this is a finite dimensional vector space. So we know that dual of C2 with L infinity norm is this is isometrically isomorphic to C2 with L1 norm. So this is a result. So dual of C2 with L infinity norm is isometrically isomorphic, means norm should be preserved. Isometrically isomorphic to C2 with non L1 norm. So via this canonical map, what is the, so this is true, and you can also, so you can check that this map is, so this, so let's T from this is the map basically. This map is isometrically isomorphic. So if psi is in 1, so let's suppose psi of z, then so this z you can write x u1 plus y e2. So psi of u1 x plus psi e2 y. So this you can think of as a two vector, psi 1 u1 comma psi e2. So this map you can define t psi to be this psi of e1 psi of e2. And what is this norm psi? Then you can, and norm psi is same as, this is the basically L1 norm of this. So this map you can show that this map is basically norm is the same, means this T is, because both sides psi and this tuple has both has norm same, so this is isometric, and you can show that this map T is also bijective continuous and inverse is continuous, so isomorphic. So C2 with L infinity norm, dual of this space is C2 with L1 norm, and this is isometrically isomorphic. So we'll use this to calculate the norm of psi. So norm psi will be and what is psi of u1? So psi of 1 0, so this is alpha 1 plus beta 0, so it's alpha, and psi of 0, 1, it's alpha 0 plus beta 1, so it's beta, so it's mod alpha plus mod beta. So we have got both the norm of phi, we have got this to be 1 and norm of psi to be this. Now as psi is a norm preserving extension of phi to C2 with L infinity norm, so norm of psi should be equals to norm of phi, means mod alpha plus mod beta is equals to 1. So let me call it 2. So what we have got? So we have got two equations. From 1, here we have got psi plus alpha plus beta is 1, and here we have got mod alpha plus mod beta equals to 1. So now we will solve these two equations. Here this alpha and beta complex number. So let alpha, we call it by A1 plus IB1 and beta A2 plus IB2. So the first condition alpha plus beta means alpha plus beta is 1, means A1 plus A2 plus IB1 plus B2. This is 1. So A1 plus A2 is 1 and B1 plus B2 is 0. So we get this. So A2 is 1 minus A1 and B2 is minus B1. Now let's put this in the second one. Mod alpha plus mod beta is 1, or A1 square plus A2 square, A1 plus B1 squared, plus A2 square plus B2 square, this is 1, or put B1 equals to, so this is B2 minus B2, so A1 square plus, so this is B2 square plus square root, A2 is 1 minus A1 square plus B2 square is 1. Now take this to be the other side and square it out. So if you square it out, what you will get? A1 square plus B2 square minus 2 square root A1 square plus B2 square plus 1 equals to 1 minus 2A1 plus A1 square plus B2 square. So if you simplify a1 square and b2 square both cancel, 1 will cancel. So what we'll get, a1 square plus b2 square equals to a1 square, or b2 square equals to 0, or b2 is 0, as b1 is minus b2, so 0. So we get b1 b2 both 0. So a1 a2 we have not got in condition, but we know a1 plus a2 is 1. So now also so what you get, mod a alpha plus mod beta 1, or as b1 b2 0, so this is a1 plus mod a1 plus mod a2, this is 1. So which imply mod a1 is less than 1 and mod a2 is less than 1. But can a1 a2 0? So if a1 is strictly less than 0, then a2, which is 1 minus a1, will be bigger than 1. So which is not possible, because mod a2 is less than 1. So 0 less than a1 less than equals to 1. Similarly, you can show 0 less than a2 less than equals to 1. So we get alpha equals to a1, 0 and a1 belongs to this belongs to 0 1, and beta equals to a2, which is also belongs to 0 1. Therefore, what is then psi? So this is the linear function. This we have set psi of z means psi of x comma y to be alpha x plus beta y. Alpha we get a1 x, beta we get a2y, where a1 a2 belongs to 0 1. Now what we have to find? Psi of 1 0. We have to find psi of 1 0. So what is this? Psi of 1 0. Then psi of 1 0. If you put, so you will get a1 into 1 plus a2 into 0, which is a1. So this belongs to 0 1. So the set psi of 1 comma 0 such that psi is a norm preserving extension of phi to all C2 with this element around. This set is equals to 0 1. Okay, so now let's check which option is correct. So therefore first option is single one, it's not true. Second one is 1 by 2 comma 3 by 2, this is also false. Third one 1 to infinity false. Last one is closed 0 1, so this is true. So option D is the correct one. Okay. Okay, so we have also solved the question number 34. Any questions? Okay, if not, then let's move to the next one. Okay, so today we'll solve Gate 2019 question. This is a question number 25. It is a question from functional analysis. So let L2 be a sequence space where entries are from complex number such that this is square summable, means mod xi square, and if you sum over I equals to 1 to infinity, this is finite. So this is a non-linear space with the norm is given by this. Then we have defined let G from L2 to C be a bounded linear functional defined by G of x equals to summation n equals to 1 to infinity xn by 3 to the power n for x is in L2. Then it is saying the supremum of mod gx such that norm x L2 norm of x is less than equals to 1 whole square is equals to, you have to find this, or this is what. So this is basically the norm of G, operator norm of the functional G. So that we have to find. Okay. So this is the NPTEL reference. This you can check. Okay. So let's try to solve this one. So L2 is given. This is sequence space. Okay, so this is L2, and what is the norm for x is in L2? The L2 norm is given by summation n equals to 1 to infinity mod xn squared to the power half. So this will be n. Yeah. Now G is from L2 to C. So this is defined G of x to with summation n equals to 1 to infinity xn by 3 to the power n for x in L2. So you have to find operator norm of G. Gx such that L2 norm of this should be less than 1. Okay. So note that first L2, this is a Hilbert space. So first, so for that we have a ridge representation theorem. So let me write down it. So we'll use ridge representation theorem to prove this one. So let T be a bounded linear functional on a Hilbert space H. Then, so it has a Hilbert space, so it has natural inert product. So then there exists unique G in H such that T of F is given by F inner product with G for all F in H, and operator norm of T is same as Hilbert space norm of G, right? So it is saying that any bounded linear functional on Hilbert space H is given by inner product with some unique function G, like this, and the operator norm of that linear functional is same as the that Hilbert space norm of that element G. So here we have this. So L2 is, as L2 is Hilbert space, and this is the linear functional. So this will be given by inner product with some element in L2. So let's see what. So L2, this is a Hilbert space, and what is the inner product on L2? So this is x1, x2. And what is the for x and y in L2? The inner product is defined by xy such that summation xi yi bar. So this because here that xi and y are a complex number. And G is from L2 to C. So this is a bounded linear functional. Is bounded linear functional given by G of x equals to xn by 3 to the power n. So as this is a bounded linear functional, so it will be given by an inner product with some unique vector. By ridge representation theorem, so this I am calling it RRT, we know g of x should be x inner product y for some unique y. So what is that element? And operator norm of G is same as L2 norm of Y. So as we have G of x is summation xn by 3 to the power n. So note that this you can write summation x inner product y, where y we take this vector 1 by 3, 1 by 3 square, 1 by 3 cube, dot 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 this, and x is this vector x1, x2. So if you take the inner product x and y, you will get exactly this G. And note y is in L2 as summation 1 by 3 to the power 2n. This is finite. So by uniqueness of ridge representation theorem, this is that y. And what will be the by ridge representation theorem? We have norm of G. So let me call it this y naught equals to norm of y naught. So what is this norm of y naught? So this should be n equals to 1 to infinity 1 by 3 to the power 2n. Now what is this? If you calculate this infinite geometric series, so it is a by 1 minus r square so 1 by 9 and 8 by 9, so 1 by 8. Now what we have to find? We have to find this. So note that what is the definition of norm G? Norm G is, or this functional norm of G is basically supremum of mod Gx such that norm L2 norm is less than 1. So this is same, right? That quantity, so supremum of mod Gx such that L2 norm of x is less than 1 whole square means this is norm G square, so which is same as norm y naught square, so it is 1 by 8. Okay, so what we have got this. Okay, so this we have to write in the round of 3 decimal places. So 1 by 8, if you do it in, write it in decimal expansion, so you will get basically 0.125. So the answer is 0.125. Okay. done question number 25. Any questions or doubt? Okay, if not, let's move to the next one. Okay, so today I'll solve a question from functional analysis. So this is a question of Gate 2019. It's question number 12. Let x and y be non-linear spaces and T be this is a linear operator from x to y which is bijective and linear with the closed graph. Then which of the following statements is true? 4 options are given. So you have to check which one is true. Okay, so in order to solve this is the NPTEL reference. This you can look into it. Okay, so let's start solving the question. So what it is given that x, y are normed linear spaces, not necessarily Banach spaces. So they may not be complete. So it is saying that such that the linear operator has closed graph. But as the x and y are not necessarily Banach spaces, so we cannot use the closed graph theorem. Because for closed graph theorem, xy we need to be Banach spaces. So first option is saying that the graph of t is equal to x cross y. So let's check that this is true or not. So option 1. So first we are given x and y, non-linear spaces, and t is a map from x to y, which is bijective and linear with closed graph. So closed graph means what is graph? Graph of a function. So graph of t is the tuple x comma tx such that x belongs to capital X. So means this set is closed in the product topology in x cross y. So this is a subset of x cross y. T has closed graph. Mean the graph of T is closed in the product topology x cross y. Okay. So first option you have to check that the graph of T is equal to x cross y or not. So let's so what is saying the graph of T, the graph of T is equal to x cross y. So this is false. Why? Let's take this example. T defined from R to R. Identity map T of x going to x. Then what is graph of T? So graph of T is x comma tx such that x belongs to R. So this is x comma x. So this is the diagonal of R cross R. So this is a strict proper subset of R cross R. So this is not equals to R cross R. So the first option is false. Graph of T is not equals to x cross y. And the next option, option B, is saying that T inverse is continuous. So B, T inverse is continuous. So first let's check why T inverse, because T is given to be bijective. As T is bijective, so T inverse exists. So this is again false, we will check. So if we are saying that this is not continuous, means we have to give a counter example. So let's take x to be the, so first define that L1 of n. So this is a sequence space such that the sequence is summable. So inside L1 we define, so let's take x to be x, and define the norm. And what is a sequence? If A is in L1, we define the norm of L1 norm of A is to be n equals to 1 to infinity mod n. Now define x. So what will take x to be the L1 with L1 norm. And we also define, and y we define another space. So this is L1 with different norm, L2 norm. What is L2 norm here? So this is square summable. So an mod square n equals to 1 to infinity to the power half. Now if a sequence is in L1, why the L2 norm will be finite? So that we need to check, right? So this you can check, that if means L2 norm is less than L1 norm. So just check this. A L2 norm is less than L1 norm. So as A we have taken from sequence from L1 space, so L1 norm is finite, so L2 norm is also finite. So this is well defined. Okay, so these two spaces are fine, x with L1 norm and y is L1 with L2 norm. Now we defined a linear operator, so you have to check that T inverse will not be continuous. So define T from x to y. This is again we are defining this to be identity map, T of x going to x. So this is obviously linear and bijective. So note T is linear and bijective. Again we have to also check that graph of T is closed. You have to check. So let's check that graph of T is closed. Graph of T is closed. So why the graph of T is closed? What is graph of T? X comma Tx such that x is in x so closed means we have to check that if you take a sequence from here and converges to some point, then the limit point should be in this set. So means we have to check let xn converges to x in x and xn converges to y in y, then to show x equals to y. And xn converges to x means, so xn converges to x in L1 norm. xn converges to x in x imply xn converges to x in L1 norm. And xn converges to y in y imply xn converges to y in L2 norm. And as we have said that L2 norm is less than y, as we have L2 norm is less than L1 norm for all a in L1. So xn minus x L2 norm is less than xn minus x L1 norm. And as this converges to 0 in L1 means xn converges to x in all x2 also. So xn converges to x in L2 norm also. And as xn converges to both x and y in L2 norm, so by uniqueness of the limit, so by uniqueness of the limit, we get x equals to y. Okay, so means the graph of t is closed. So graph of t is closed. And this is as bijective, so inverse is well defined. Now you have to show that inverse is not continuous. Now we have to check T inverse is not continuous. So we will prove this by contradiction. So let us assume that suppose T inverse is continuous. So where is map? T inverse is a map from what to where? So T inverse is a map from y to x. Is continuous. Okay, then what is the, for linear operator, what is the definition of continuity? So means T inverse of A L1 norm is less than C times A L2 norm for all A in Y and for some C positive. Okay. So suppose this hold. So let us rewrite it again. So what is this? So L1 norm means as T inverse is identity map. So A L1 norm, this is saying that let's C times A L2 norm. Means L1 norm should be less than C times n equals to 1 to infinity. So this should happen for all A in Y. Right. So we will show that this is not possible. So let's take this. So take FM, this sequence. So let's take this point first. Take 1 half 1 by 3 dot 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 1 by n and 0. So this is in y, right? Because this is 0 after finite element term. So this is in finite with respect to L2 term. So this is in y. So put this in this equation. Putting this n star, we have summation n equals to 1 to n 1 by n should be less than c times summation n equals to 1 to n 1 by n square. Now we know that right hand side is finite because it is the summation 1 by n square, which is, and now take n tends to infinity. So this is true for any n. Note this is, oh, now we can vary n. Now if we vary n, now if we take n tends to infinity, then what will happen? Then the left hand side we know as summation n equals to 1 to infinity 1 by n diverges, but summation n equals to 1 to infinity 1 by n square convergent. So one cannot be true, so one cannot hold. So this is a contradiction, right? Because this cannot hold, because if you increase n, then the left hand side will become infinite, but right hand side is always finite. So one cannot hold means what we have. So this is contradiction. So why we get the contradiction? Because we have assumed that T inverse is continuous, means such inequality holds. So therefore T inverse is not continuous. Therefore T inverse is not continuous. Okay. So option 2 is again false. T inverse is not continuous. Now let's check the third option. The graph of T inverse is closed. Graph of T inverse is closed. So we'll show that this is true. So what is graph of T inverse? Graph of T inverse, this is y comma T inverse y. So this is y comma y cross x such that y belongs to capital Y. So to show graph is closed means we have to take two sequence. So let yn comma T inverse yn, this belongs to graph of T inverse, such that yn comma t inverse yn converges to some point, let's say y comma x. So then to show y comma x belongs to graph of t inverse x, which is same as the t inverse of y equals to x, or this is because t is bijective, this is same as t of x equals to y. So this we have to show that t of x equals to y. And what we have assumed that yn, this we have assumed yn converges to this. So what is the meaning? So we have yn converges to y and t inverse yn converges to x. So let t inverse yn equals to x, xn, means yn equals to t of xn. So t of xn converges to y and xn converges to x. Now, but t is closed, but as graph of t is closed, so this is the definition of the closed graph, right? What is the definition of closed graph? If xn converges to x and txn converges to y, then t of x must be y. So t of x equals to y. So that we have to show, right? T of x equals to y. So therefore we are done. So graph of t inverse is closed. Okay. So we have shown that the graph of t inverse is closed. So this is true. Now what is the last option? The t is continuous. So again we saw that this is not true. This is also not true. T is continuous. So as early, let's take again the same example. You recall example from notation from option B. What was that? X is L1 with respect to L1 norm. Y was L1 with respect to L2 norm. Now here we will define, let's define. Here we will switch between x to y. So there we have defined t from x to y. Now we will define t from y to x. T from y to x. Again the same map, t of x equals to x, identity map. So we will show that t is not continuous. So again you can show that the graph of not t is linear and bijective. As option 2, option B, we can show Means this is the same, because there is also the identity map. You can show that this graph of T is also closed. So this operator satisfies the hypothesis of our problems. Now we have to check that the T may not be continuous. So this example, T is not continuous, but it's satisfying the hypothesis. So T is not continuous. Now we will show that T is not continuous. So again we prove it by contradiction. So suppose T is continuous. Suppose T from Y to X is continuous. Means, what is this saying? Because Y is with respect to the L2 now. So T of A, which is in X, so its L1 norm should be less than C times A L2 norm for some C positive and for all A in Y. So this is same as, because T is identity, so T of A is A, so L1 norm is less than C times A L2 norm. But so this is again same as n equals to 1 to infinity an less than C times but as early, so this is same argument as we have seen earlier, that take this and then again, because this is the same thing we have to show that this can't happen, because if you take, then the left hand side will goes to infinity but right hand side is finite, so this is not true. So this is not true. As shown in option B. So this cannot hold. So T is not continuous. Okay. So what we have got? That graph of T is equals to X cross Y, so this is false. T inverse is continuous, this is also false. Graph of T inverse is closed, so this is true. And T is continuous, so this is also false. So only option number C is the correct option. Okay. Okay, any questions or doubt? No doubts? Any question? Any other question? Okay, so we can stop for today. So again in the next week we will take 2 hour class. Okay, so let's stop. We'll again meet in the next week.